Hey there, folks. Happy Friday. Let's finish the week with just one last short problem. We have a rat and a mouse that are clinging to opposite ends of a rotating rod. And our job is to use energy conservation to determine the speed of each animal once they move into a vertical position. Now, I'll admit, I'm not the best when it comes to drawing animals, so let's pretend like these circles here represent a rat and a mouse. We're told that the length of the rod is 80 centimeters, which should be converted to meters. We're also going to need the distance from the pivot point to each animal, so let's divide the length of the rod in half to get 0.4 meters. Once we release the system from rest, everything will rotate along a circular path, with the rat ending up at the bottom and the mouse at the top, due to the difference in their masses. Let's call the rat's final position at the bottom y is equal to 0, which means the initial position for both animals was at y is equal to 0.4 meters. And of course, the mouse's final position here will be at y is equal to 0.8 meters. Now we can move on to the conservation of energy. The rat and the mouse were motionless at the beginning, so the initial kinetic energy has to be equal to 0. There's no work being done by friction or anything else that we need to worry about, so that term reduces to 0 as well. Similar to what we saw in the first problem of this chapter, there's two objects in this system with their own individual energies, which means we'll need to apply the remaining terms in our equation to each animal. Since we set the rat's final vertical position to y is equal to 0, it won't have a final potential energy. That term can be removed. There's nothing left that we can eliminate, so let's take this remaining equation and start plugging in some definitions. Before we start with the algebra, I'd like to take a quick moment to focus on something found on the right-hand side. I've used the same variable for the final speed of the rat and the mouse, as you can see here. Let me explain why that's the case. Here's a reminder for the centripetal acceleration of an object moving along a circular path. Since the animals are hanging on to the same rotating rod at the same distance from the pivot point, their accelerations also have to be the same. So in the context of this equation, if you have two objects with the same centripetal acceleration located at the same rotational radius, well, then they must have the same velocity as well. So that's why we can use one variable for both animals. With that said, let's start solving for v sub f. I'm going to factor out g and the initial y position of both animals on the left-hand side here. And we can also save on some writing by combining their masses and calling it m total, like this. Next, we can move the final potential energy of the mouse over to the left-hand side. There's a g in that quantity too, so let's continue with that factoring pattern and bring that outside. Speaking of factoring, we can pull the final velocity squared of both animals out on the right, followed by that 1/2 attached to both of their masses. Remember that we're calling the sum of both masses m total, so let's rewrite that as well. If we multiply both sides by 2, then divide both sides by the total mass and take the square root of both sides, well, then we're all set to finish things up. Go ahead and plug in the numbers, and you should arrive at the correct answer, which is 1.83 meters per second. Pretty easy, right? Thanks for watching, everybody. I hope you all have a safe weekend. I'll see you all soon.